Hello chemists, this is Ms. Placino and you are watching Screencast 5.1 on naming ionic compounds. Today we're going to discuss how compounds are named and how you can determine the chemical formula when you're given the name. In class we started off with this do now. How did you get your name? What does it mean? And some of your classmates had some interesting stories about the significance of their name and why they were named that. And we're going to try to make some connections between the meaning of your own name, if there is one, and different names of ionic compounds. So we're going to start off with binary ionic compounds. And binary, hopefully you know, means two. The prefix bi means two. And we're going to be looking at exclusively ionic compounds today. We'll save covalence for tomorrow. An ionic compound, remember, is a metal and a nonmetal joined together, or just, I guess a little bit more generally, a cation and an anion bonded together. So hopefully this is one that you're very familiar with. NaCl. The name of this compound, as you know, is sodium chloride. If you had to explain to somebody how you named this, we know that Na, for example, is sodium. We know that Cl is chlorine. So you could probably say, okay, when you're naming a binary ionic compound, the metal is going to keep its name. By convention, the metal or the cation is always listed first. You're going to change the ending of the nonmetal to "ide." So we drop the ine on chlorine and replace it with "ide." And we never use prefixes to denote subscripts. So we don't call this like monosodium monochloride because there's just one of each, because the sodium ion is going to be Na+, and the chloride ion is going to be Cl-. It's implied that there is going to be a 1-to-1 ratio. Let's do the opposite. Let's see if we can take a name and turn it into a formula. So barium bromide. What you want to do is get the names of the symbols of the element. Barium bromide comes from barium and from bromine. Barium, if you check the reference table, is a group 2 metal. So when it forms a cation, it's going to lose those 2 valence electrons and become Ba2+. Bromine is a group 17 nonmetal that's got 7 electrons in its valence shell. We know when it becomes an ion, it's going to gain an electron, get that -1 charge for a total of 8 electrons in its valence shell. We talked about this the previous unit. Put the 1 there. We're going to use the crisscross methods where the charge of the ion becomes the subscript for the opposite ion. So the charge of the cation becomes a subscript of the anion and vice versa. And we can predict Br2. Oops, and in fact, that's exactly what it is. Sorry, I've got writing over the top of it. So we need to find the charge of each ion. We just talked about the crisscross method. The charge of the ion becomes the subscript for the cation and vice versa. And we're going to reduce the subscripts to the simplest ratio. We don't need to do that here, 1-to-2. We can't reduce that down any smaller. In your workbook, you've got some practice problems, so why don't you pause the video, try these out, and we'll check and see how you do. All right, so number 1 is MgF2. That would be called magnesium fluoride. 2, LiBr, is lithium bromide. K2O is potassium oxide. SRS is strontium sulfide. If we go in the opposite direction, we've got the formula names, or I should say the compound names. Let's predict the formula. Sodium fluoride would be NaF. Sodium forms a +1 ion. Fluorine is going to become a -1 ion when it becomes fluoride. Potassium phosphide is K3P. Magnesium oxide is MgO. Mg is going to have a charge of +2. Oxygen will have a charge of -2 when it is an oxide ion. So those 2's need to cancel out. I know that technically it looks like it's kind of the same if we write Mg2O2, but the convention is to reduce down to lowest terms. So we can't use Mg2O2. We have to represent it simply with MgO. And finally, calcium nitride is Ca3N2. Let's make it a little bit more interesting. Let's talk about ionic compounds that have transition metals in them. If you take a look at the group 1 and 2 metals, and you look on the periodic table in the upper right-hand corner, you'll see that all of them just have one possible charge or oxidation state listed. However, if you look at the transition metals, the D block elements in the middle of the table, you'll see that many of them are able to take on multiple oxidation states or multiple charges. For example, if you find manganese, Mn, you'll see that manganese can take on a variety of different charges. So we want to figure out which manganese this is. So hopefully we can look at this and recognize that it's going to be some type of manganese oxide. But if you were to go to a chemical supply company and say, I'd like to buy some manganese oxide, they're probably going to ask you which one. Manganese can take on a variety of charges, so we need to specify. In order to figure out what the charge of the manganese ion is in this case, we need to look at the subscript of the anion. We know from the crisscross method that the subscripts come from the charge of the opposite ion. So we know that an oxide ion is going to be -2. In this case, the manganese ion must be +3. And to represent that, we're just going to put parentheses and then the Roman numeral 3, so just 3 capital I's in parentheses. So we'd call this manganese 3 oxide. So the subscript of the anion comes from the charge of the cation. And since the cation can have multiple charges in these cases, you need to specify. So use the Roman numerals to get that, to specify which manganese ion you're talking about in this case. Let's try the opposite direction. We've got cobalt-2 fluoride. Ooh, sorry about that, didn't mean to zoom in. CO2 plus because of cobalt-2. Fluoride ions have a charge of -1, so when you use the crisscross method, we end up with COF2 for cobalt-2 fluoride. Remember, the Roman numeral is telling us the charge of the cation, and often that's going to be the subscript of the anion unless things have been reduced down. Again, reduce the subscripts to the simplest ratio. We'll always see that when we're expressing formula units for ionic compounds. So just like last time, there's a whole bunch of practice problems for you to work with. Pause the video, try these out, and we'll check them over together in a minute. All right, up first we have CO2S3. This is going to be cobalt-3 sulfide. Remember, the subscript of the anion is going to be related to the charge of the cation. TiF2 is titanium-2 fluoride. NiCl3, nickel-3 chloride. Be careful with number 4. If we think about this, when you first look at it, it looks like it might be chromium-3 oxide. That is not the case. Chromium, we're trying to figure out its charge. We know that the oxide ion is always a -2. So in order for this to reduce down to chromium, CrO3, we must have chromium with a charge of +6. That way when we do the crisscross, we get Cr2O6. So we can simplify that to CrO3. Be careful. This happens a lot when we're talking about the group 16 nonmetals, so things like oxygen, sulfur, selenium, and some of the polyatomic ions that we'll discuss later in this video. Copper-2 chloride, CuCl2, platinum-2 sulfide. This one's going to reduce down. It's just PTS, +2 for platinum, -2 for sulfide, so it's going to be that 1-to-1 ratio. Iron-3 oxide, more commonly known as rust, is Fe2O3, and lead isn't a transition metal, but when you look up lead on the periodic table, it can have a +2 or a +4 charge, so we need to specify which we're talking about. Lead-2 bromide has the formula PbBr3. Okay, so now let's talk about ionic compounds that have polyatomic ions included. So far we've looked at simple binary compounds where there's just one cation, one anion. Generally, it's going to be a metal with a nonmetal. When we're talking about polyatomics, hopefully you know from English class that the prefix poly means many, and you could probably guess that the word atomic is referring to atoms. So polyatomic ions are ions that are composed of many atoms. For example, if you've got NaSO4, we have the sodium atom, or in this case, the sodium ion. And then this SO4 is a polyatomic. In this case, we have sulfate. You can look it up in table E on your reference table. And you can see that this is, well, it's called sulfate, and it has a charge of -2. So I would simply call this compound sodium sulfate. One thing that you want to make sure you're doing when you're naming compounds that have a polyatomic present is that you never, ever, under any circumstance, change the name of a polyatomic ion. Before, we were taking endings and we were dropping them and adding "ide." Usually the endings for our polyatomics are going to be "ate" or "ite." Leave those alone. Do not change them. If we go in the opposite direction, let's take calcium nitrate. So we have calcium, which will form a 2+ ion. If you look up nitrate in your reference table, it is NO3 with a charge of -1. So when I do the crisscross method, I'm going to get calcium nitrate as Ca parentheses NO3 close parentheses 2. If you need multiple polyatomic ions, you're going to use parentheses. You can think about it as kind of protecting the polyatomic. If I did something like this, well, that looks kind of ridiculous. Looks like you have calcium, a nitrogen atom, and you've got 32 oxygens. So that's not going to work. We also don't distribute through the way you would in math class. I wouldn't want to say this is CaN2O6. I know that's kind of in some ways communicating the same thing, but this nitrate ion being written out this way, NO3, is giving us a little bit of information about the structure of that ion. So we never really want to distribute through like you would in math class. Use the parentheses and never really play around with the subscript of a polyatomic. Oop, there we go. Let's erase this. So treat the polyatomic as a single group. Do not alter the subscript. So again, we're going to use parentheses when you need multiple polyatomic ions. That way you can have the 2, in this case, outside of the parentheses, and you're telling us, okay, I have 2 nitrates present. Let's try some practice. Use table E, pause the video, try these out, and we'll check them over together. All right, so we have Sr parentheses Cn2. This is going to be strontium cyanide. Number 2 is NH4 parentheses 2. This is one of the rare polyatomic cations that we have on table E. That's going to be called ammonium oxide. Number 3 is aluminum sulfite. Be very careful about your spelling. I'm sure that sounds weird coming from a chemistry teacher, but there's a difference between sulfite and sulfate, and it's an oxygen atom. So you really want to make sure that your endings are correct. Ag2CO3, that's silver carbonate. Silver only has one possible charge, so you don't have to use any parentheses around it in Roman numerals. Lithium chromate would be Li2CrO4. Calcium acetate. On the reference table, it looks like there are 2 different acetates to choose from, but if you look carefully, they're actually expressing the same thing. As a chemist, I like this format better because it tells me a little bit about how the acetate ion is actually structured, but I don't care which one you use. As long as you have a ratio of 1 calcium ion to 2 acetate ions, I'm happy. Barium hydroxide. Make sure you've got the parentheses around OH. I see a lot of students just write this. It looks very similar, but it's not the same. This is saying barium, oxygen, and 2 hydrogens, and what you really want to communicate is barium and 2 hydroxides, so that it's not okay. Make sure you've got parentheses. And finally, cesium hypochlorite is CsClO. All right. There is a flowchart in your workbook that has you it's set up to help you figure out naming ionic compounds. So there are 2 large boxes. You can have 2 yes or no questions that go in each of those. And then in the 4 smaller boxes, write what impact the answer to those questions has on naming the compounds. Really, the key when you're naming ionic compounds is to look out for polyatomic ions and to look out for metals that can have multiple charges. It's really easy to kind of put it on autopilot and try to just blaze through naming. You want to slow down and be careful. Make sure that you have the correct charge for the anion and the cation. Make sure that you're selecting the right polyatomic and the right ending if you are naming. And this is something that's just going to require a lot of practice. So if you look at your workbook, you have like 20 different practice problems just on naming ionic compounds, and you're really just going to want to get those repetitions in until you become comfortable with it. All right, that's it for today. I hope you found this video helpful, and thanks for tuning in.